Hi everyone, we are back and let's get into our Pset 4 solution. So I'm going to do a diffusion couple and it's going to be made of a mystery material here, X on the left, Y on the right, and after a long time at high temperatures I form pores here. So let's draw the diffusion profile. So I know if pores are forming here, I have more material X leaving than is being replaced by Y or extra half plane, so I know my diffusivity of X is greater than my diffusivity of Y. And I know that in my C frame, I'm going to have the flux of X, Y, and vacancies. They all must sum to 0. So I know X is going to flow from here to here. Flux of X in the C frame, it goes in that direction. Y, flux of Y in the C frame, and then now flux of vacancies must adapt here. So I have lots of materials going here, filling up those extra half planes. Adding extra half planes. Here, extra half planes are being gobbled up by vacancies and thus creating pores. So I'm expanding over here. I'm contracting over here. So my interface is going to move in the direction of the flux. So that's my interface motion. Since I know the diffusivity of X, which I'm going to do as a dashed line versus a solid line here. If I look at the concentration profile, this is 1 or 100% as a function of X. My X will be 100, and then as we get to this kind of halfway point right here, it will have some non-zero value here, whereas my Y is going to be 100% here, and then it will never basically diffuse in. So I've got diffusivities, diffusion profile or concentration profile. Which material is smaller? Probably X if it's diffusing larger. Which has large solubility? X into Y. Got it. Qualitatively and quantitatively, difference between intrinsic and self-diffusivity. So that's in our notes. We looked at, again, it's a function of that chemical activity. What is the flux condition in the C frame? So we know that in the C frame, I need X plus Y plus vacancies in C frame must sum to 0. Hence why the magnitudes are the same. So got this. Draw the fluxes, got it. What direction will the interface move? We described that. How would you calculate the velocity of the interface motion? Again, that's given in the notes as well. Excellent. So, calculate the activation energy of Ag. So, I'm given a plot of Ag concentration versus penetration depth. So, let's just say I want to pick a concentration like this. So, I'm given depth. So, we know from our notes or lecture notes for dt, this is my engineering approximation. So I could figure out the depth x, and then we see here all of these are for times, annealing times of 30 minutes. So initially this is my as implanted. So my as implanted depth is about 2 micrometers. If I look, and let's just say, let's look at red for example. If I look, actually forget about red. Let's look at let's look at here. So at 1000, I have a depth of about 7, and at 1150, I have a depth of about right here. So I know that diffusion is equal to d naught exponential minus qa divided by kt. So I know I could solve for diffusivity based on x and t and the d here. So let's go ahead and let's start to kind of solve for this function. So let's say I'm going to solve for, so we said that my x1 is going to be equal to, what is it? It's 7, but I've already started 2, so it's actually 5 times 10 to the minus 6. So the as implanted is 2 micrometers, so when I go 7, I've only traveled 5. And the same thing for my x2. My x2 is going to be equal to 12 times 10 to the minus 6. My t1 is going to be equal to 1100. Plus 273. My T2 is going to be equal to 1150 plus 273. And then I've got the X, I've got those values here. Now I can kind of go ahead and start to solve. Actually, let me see, my time is going to be equal to 30 minutes times 60 seconds per minute. So I've got all those values, meters, Kelvin, so I'm now good to go. So I'm going to solve X1 set equal to square root of 4 times d1 times t. So I want to solve this for what is my d1, and let's do numerically solve it. So I've got that. What else do we got here? So 1 second here. I'm gonna go, excellent. So I can also solve for my d2. So x2 d2 time is the same. Oops. Let's solve for d2. So this will be my d1. So d1 equals this. d2 equals this. And then now I could go about and solve where d1 set equal to d naught times exponential of minus QA divided by my K is going to be equal to my Boltzmann's constant, 1.38 times 10 to the minus 23 over K times T1. There we go. And then I'm going to copy this and just do the same thing, but for my D2, T2. D2, T2. I want to solve for D naught, QA, and I want to give me my real values, my reals. And there you go. So I'm going to write these down right now because they may come in handy in just a second. So those are my values, at least the ones that I've calculated. All right, excellent. So I now want to coat a stainless steel surface with a 50 nanometer film of AG. I have 8 hours to complete the process. What is the lowest temperature I could operate at? So my X is effectively going to be that 500 nanometers. So I'm going to use that same equation again. So I need to solve for, I have 8 hours, so I need to solve for 500 micrometers, 500 times 10 to the minus 6. Set that equal to square root of 4 times D, diffusivity times time, which is going to be 4 hours, or 8 hours, excuse me. So 8 hours times 60 minutes times 60 seconds. And I want to solve for D. So that numerically solve it. All right. So that's my diffusivity, and we know my diffusivity equation. So let's go ahead and solve. And we know this set equal to D naught times exponential minus QA from what we solved previously divided by K times T. And let's solve this for T. And voila, pretty high temperature. Anyways, all right. So for that same problem where we had our stainless steel and we're shooting in our AG, I want you to solve for the concentration of AG as a function of distance. So I'm going to say that this is x equals 0, this is 500 micrometers. Solve for the concentration and plot it at several times. So I need to write out boundary conditions, PDE, ODE. So I'm going to use, this is my PDE in class, assuming we're 1D. My ODE is going to be eta is equal to x divided by square root of 4 dt. My ODE is this, d squared c, d eta squared. Once I do my chain rule and all those things, dc d eta equals 0. So what are my boundary conditions here? Well, one of the assumptions I'm going to make is that I'm semi-infinite, and that will hold as long as L is greater than 10 root dt. So this holds as long as that condition is met. And actually, we could look at for what times and temperatures that is, depending on the values. But here, my concentration of Ag at eta equals 0 would then be equal to 1. My concentration of Ag at eta equals infinity would be equal to 0. And if I were to plot the concentration of Ag at a value of 1, and then basically here's my eta or x effectively, you would basically see something like this. So at very short times, it would look like this. And as time increases, again, I still have my ending points here that are fixed. So like that. So this is where time is increasing. Excellent. I have CAF2 and I want to insert BF3 into the material to change the band gap structure and create new electrical magnetic properties. It could form Frankel, all of these types of defects, but we see the Schottky defect as the lowest energy. So we want to plot effectively how does the natural log of vacancies of F, and let's see, we should know that vacancy of F is going to be basically a plus 1 log of concentration of this, 1 over T, we know that this is intrinsic, this is extrinsic. And then let's zoom out a little bit, versus the log, again, 1 over t ln of diffusivity of f. And we know that diffusivity is going to be proportional to basically the number of sites that I can diffuse into, gamma r squared f over 2d. We don't care about this. It doesn't scale temperature this or this. And then we're left with these two parameters, and we know that our gamma scales as exponential minus g migration over kt. So we have those values. So first off, I have BF3. So I want to write out the intrinsic reactions of BF3 that are shocky. So BF3 is my host. So I'm going to do my first step, null goes to vacancy in F, which is going to be plus here, plus vacancy in B, minus 3 times 3. So that is my reaction. So 2, I need to write my K shocky, which is equal to exponential minus G formation of shocky over KT, which is going to be equal to concentration of VF here to the third, VB to the 3 here. I'm going to write my charge neutrality statement. So basically, or electron neutrality statement, same thing, equals 3 VB to 3. Then finally, do my math, plug equation 3 back into equation 2 here, because I want the concentration of vacancies in fluorine. So when I do that, actually you can see that right here, I am going to get basically something that's proportional to, or approximately VF to the 4th is proportional to exponential minus G formation of shocky over KT. I'm going to get rid of the 4th here, put the 4th there, and then now I'm good to go. So my slope here is minus G formation of shocky over 4K. My slope on the diffusion for the intrinsic high temperature region is going to be that minus G formation of shocky over 4K minus G migration over K. And that's it. What about the extrinsic when I'm putting in CaF2? So when I put CaF2 into BF3, I need to make sure I create a vacancy in fluorine, which is a plus. And then if I do plus a calcium, substituting on a B, so 3 to 2, so that's going to be a minus. So let's go over here. And then I need to do plus 2F FX. So CaF2, good. What about those? Great. And then now I could just do my 1, 2 electron neutrality. The vacancies in F are going to be equal to BF3, good, to my concentration of CaB, right, like this. So those are my electron neutrality statements. So in my extrinsic, there's no temperature dependence. In fact, it'll just be basically the log of CaB here. And then, but for my diffusion, I still have the minus Gm over K. Excellent. Now let's get into the next one, and the last one in this problem statement. So I have UO2, I want to insert it into MgO. So let's go ahead, let's play around with this guy. Delete, delete, delete. Actually, I could just erase here. Actually, I'll just read it. So let's zoom in a little bit. So I want to label 1 over t again. So the natural log of what? Vacancies in U, which is U is, actually, I have UO2, so vacancies in U is going to be a minus 4. And then I'm going to have the natural log of the diffusion in U, 1 over T, intrinsic, extrinsic, intrinsic, extrinsic. And so now I see again the shockies are the lowest. So my shocky defect for UO2 is going to be null goes to vacancies in U, 1, 2, 3, 4, plus vacancies in O, which is here, going to be 2 here. My K shocky is going to be equal to exponential minus G formation of shocky over KT, which is going to be equal to vacancies in O squared times vacancies in U, 1, 2, 3, 4. My electroneutrality, 4 times vacancies of U, 1, 2, 3, 4, equals 2 times vacancies in O. Boom. And then my last step, plugging that back in, I'll get some expression. Again, I could just look at this by inspection that vacancies in oxygen to the third is going to be proportional to exponential minus G formation of Schottky over K T. Take that, put the 4 there, so my slope, or excuse me, the 3. Excuse that, not 4, 3. So minus G formation of Schottky over 3K. Diffusivity, again, I need to add 3K minus GM over K. I have to add that. Extrinsic reaction. So I want to insert MgO into UO2. When I do that, I need to make sure I have what? A vacancy in U. 1, 2, 3, 4. If I substitute Mg on O, that's going to be an issue. So I'm just going to do an Mgi, which is going to be 2 here. I'm going to do 2. And then I need 2 oxygen, oxygen X. So 2 Mg, O2, UO2. I'm good to go. My electroneutrality statement is going to be what? It's going to be 4 times U vacancy, excuse me, in U, 1, 2, 3, 4, equals 2 Mgi, 1, 2. There. So again, no temperature dependence here, but there is a minus GM over K right here. And that's it. So that is your Pset 4 in a nutshell. So thank you, and I will see you all next time for Pset 5. Bye.